All right, welcome everyone to part two, or I guess part three if you include the introduction. So what we got here is we're going to take a look at working with square roots, cubed roots, as we called them, radicals, and surds for the British version there. The what we got, two sections here, or kind of maybe three because we got to look at these square numbers, cubic numbers. Just as a heads up to what these things are in case you've seen them before. Creating mixed roots, that's if you're given something like this, right? This isn't mixed, by the way. And then switching it, doing the work, the good looking algebra, so you get an answer like this. This is this is called an entire radical. Entire is like whole thing. Whole thing is underneath. And then this is the mixed radical, mixed up because part of it is in the inside and part of it is on the outside. So that's what creating mixed mixed radicals are. The second thing is adding or subtracting. And so just as a reminder, if you have something like that, 5 root 3, that gives you 7 root 3. Just in case, as I said, you've seen the topic before, but maybe don't recognize the words there. And I'm going to tell you straight up, there's one thing I don't recognize. It's not creating mixed roots. It's creating mixed radicals. Roots are something else. Same down here. Adding or subtracting. Oh, there you go. That's what happens when you too aggressive. That should be radicals there. Square roots, yes. Cubed roots, mixed radicals. Okay. So if you know this topic, then yeah, you can skim your way through the videos, complete the worksheets, but otherwise, yeah, here we go. A couple of bits for a couple of things to look at. Number one, what do we got? Just a reminder what perfect squares are, or show you what perfect squares are. These are numbers where the exponents are all even. And so as a reminder, even numbers are all multiples of 2. You got 2, 4, 6, 8, 10, etc., etc. The odd numbers are all the other ones, 1, 3, 5, 7, 9, like that. Okay, so just as, and I think you probably know this from your elementary school days, 25 can be same as 5 times 5, right? With exponents, looks like this. 100, we worked on this before. 400, that's new, but you do the prime factorization, tree or repeated division, and you can get this prime factorization. Right, I guess notice usually the small number is first. I think just for typing ended up this way. Not wrong, but just kind of weird looking. But importantly, perfect squares, even exponents. Okay, these are all multiples of 2. 0 and 1 are always special. So yes, 0 squared is 0. So that can count as a square number. 1 squared, yes, is 1. So that can count as a square number as well. But I guess as I mentioned, 1, is it prime or not? No, it's not. It's different in a different way from prime numbers. Okay, but that's not really the point of this topic right now anyways. Okay, just taking a look at squared numbers and also take a look at this, cube numbers. Okay, a perfect cube. These are numbers that have exponents of multiples of 3. So a multiple of 3 right? What do we got? 3, 6, 9, 12, 15. Right, all these are multiples, numbers that are multiples of 3. So if you do the prime factorization, it's kind of a shorthand, prime factorization, and you get something like a 12 showing up there. Well, is 12 a multiple of 3? Yes, it is. So is this thing a cube number? Yes, it would be. Right? If it's something else like a 14 or a 7, that's not a multiple of 3, then no, not cubed. So these numbers are starting to get a bit, perhaps a bit big, but looking at 512, as a math teacher, I recognize that one. 216, a little more awkward, even though I'm a math teacher. But nonetheless, this is how you can figure out if something is a perfect cube or not. Find the prime factorization. Take a look at the exponents. Okay. If there's 3's all over the place, cube numbers. Special attention to these ones again, and yes, they also count. Now this steps away from working with radicals a little bit, but related. There's a whole branch of math called number theory, which is about how numbers work, how they relate to one another. And so this is like a number theory type question, because it's a question about the math of the numbers, if you like. 0 and 1 we saw are both perfect square and a cube, perfect cubed. 0 squared is 0, 0 cubed, 0. Same with 1. 1 squared is 1, 1 cubed is 1. So these numbers are both. Number theory question, any other numbers? Yes. What to look for? Well, for them to be a perfect square, the numbers have to be, that is the exponents have to be even, a multiple of 2. And to be a perfect cube, the numbers have to be a multiple of 3. Importantly, at the same time. So how does this happen? Well, you can imagine then, if it's both a 2 and a 3 upstairs there, and the exponent, and in fact what we're looking at are multiples of 6. Okay? That multiple of 6 would be both even, and so a square, and it would also be a multiple of 3, so also a cubed. So you can put any number down here for the base, that the 5 is. Oh, any positive number for us, if you don't mind. And as long as you have a 6 or a 12 or an 18 up there, the numbers you get will be both perfect square and a perfect cube. Congratulations. Number 1, or your first number theory fact. But let's get back to radicals, square roots. There are a couple of ways to solve these, to work with square roots, to work with radicals. And one of them needs, you need to know about the squares and the cubes. So check this out. First of all, if you had, look at the screen here, if you had a question that looked like 3x is equal to 12, you can divide both sides by 3 and you get the answer. Happens to be 4. Or check this out. What you can do is multiply by 1 over 3. What you do to one side, you do to the other, of course, keep things equal. Now, what'll happen is the 3 in front here will be divided out by the 3 on the bottom here. So in fact, these are, you can think of them as inverses of one another. Inverses is like the math word for opposites. Not the only math word, just because of the different situations that come up. But yeah, 1/3 can count as the inverse of 3. What happens when these combine together? They're gone, right? What are you left with? X only. So they divide out, they make one another disappear. On the right-hand side, you just work it out and you get it. So looking at the left side with the square roots and the square, those are opposites of one another. They'll make one another disappear. With the cubed root, same thing. They will make one another disappear because there are opposites with one another. And there's a proper and professional way to show that, but we're going to do that in a little later on. Do the friendly version to start with. Here, this is just a few examples showing how squares and square roots are related. So you see squaring 3 makes it bigger. Square rooting makes it smaller. Squaring the 3 gives you the 9. Square rooting the 9, the opposite, gets you back to the 3. Squaring the 5 makes it bigger. Happens to. If you have decimals, it's different, but that's okay. 5 squared gives you 25. Taking the square root, it undoes that. Gets you back to 5. It's the opposite. Then to start getting a little fancier, bigger numbers, kind of a cool pattern. Right? If you cube 111, if rather not 111, but 11. 11 cubed. That's the same as 1331. So you undo it. I don't know if you can see that, but that's a 3 right there. A tiny 3 like that. Like this. This is better, more professional. Cubed root, 3 over there. That's equal to 11. Just opposites. So with that in mind, we can actually get started on doing some multiplying, perhaps dividing later. Probably stick with multiplying first here. Now, there are long ways and short ways. Check this out. I'm just showing you, I'm going to show this a couple of ways. One is just to remind you how these, or to show you how these square roots work. But keep in mind, if the goal is to get the final answer, you can get it pretty quick. Okay, so what do we got here? Square root of 3 times square root of 25. Well, hopefully you know the square root of 9 is, square root of 9 rather, gave you the answer. Square root of 9 is 3. Square root of 5 is, square root of 25 is 5. So effectively you got a 3 times a 5, which gives an answer of 15. Okay, so let's check it out. Now, I know for a fact that this is written differently, just to show you what the properties of these square root things are. Okay, so this is the first version, actually the version I just said, so not differently. But I think in the next slide it is. Yeah, so notice down here, instead of doing the square roots first, right, you can multiply the insides together first. So that's a second way of doing it. See, because they're both square roots, you combine them both together. 9 times 25 on the inside. What does it work out to be? 225 from your brain, 15, and you get it worked out there. Okay, so some ways definitely are better than others. If I had to solve this, I would do it the first way. But again, just for teaching methods in this topic, showing you can do it this other way. And then showing you this math fact here that square roots have this property where you can take them, where they're separate, you can combine them both together. Or similarly, the other way around, if they're both together underneath the square root, you can separate them into two separate square roots that are multiplied together. Okay. The important property of square root wanted to show you. Second example, same style, right? We got this. Could multiply it all out. 3 times 3 is 9. 5 squared, 25. I think it's the same question. Okay, but just to show you here. Just to show you. See, there's a missing part. Little blank in there. Have it all together. So algebraic wise, this is the missing piece. Using what I just showed you, you can split them up. Split the inside up into 2 separate square roots that are multiplied together. And then remember, there are opposites of one another. Inverses being the official word. Square root of a square, just a number. Square root of the square, just a number. Multiplied, multiplied. 15, just as it shows you on the left side screen there. $100, boy, in real life, you better be fast, right? This one, 2 seconds. What's the square root of 100? 10. Done. But just to remind you of the properties and actually start tying into some more different style of questions. The square root of 100. This is the missing part. This is the same as 25 times 4. And in fact, we can put another piece in there, right? Because 25 is the same as what? 5 squared. 4 is the same as what? 2 squared. And now we're back onto the screen as it has. Now that's there. Splits up into 2 separate square roots. Squared and square root, they're opposites. Square and square root are opposites. Final answer after a lot of algebra, we get the answer of 10, right? Okay, so understand. Doing some calculating, square root of 10, super fast, but you should be able to follow along with what's going on with this algebra, because with other questions, you might be using it. Right, so going here, what do we got? Right, got the missing piece. Yeah, that's everything. Good. Now this is just different because it's a cubed root now. So what do you do with this? Well, you might know what the cubed root of 64 is. 4, by the way. But if not, then you kind of got to figure it out a different way somehow in order to get this thing. All right, so what can we do? Well, notice 64 can be written as the same as 2 to the 6. How do we do that? Prime factorization. Okay, make the factor tree, do the repeated division, and you can get this as a result here. All right, now this question might be a little out of order. Here's what we can do. 2 to the 6 cubed rooted. Yeah, this is a sneak look at a later topic. You see how this is a 3 here? That's the same as 1 over that same 3 on the outside. These multiply together. 2 to the 6 over 3 because of this exponent rules. What do you get? 6 divided by 3 is 2. Final answer, 4. Okay. Now, oh, look at this. What do we do with this thing? Prime factorization for sure. I don't know what this thing is. Work it out. Voila. All right, work it out. You get these. 2 to the 3, 3 to the 6. This 3 on the inside is undone by the 3 on the outside, so it leaves you 2 only. 2 only. This 6 on the outside, kind of like I just showed you here, changes to 2 from this 3, just by the same process, actually. All right, so it gives you the 2 there, and you work this out. 2 times 3 squared gives you 18. Okay, in fact, what I can do is I can show you the middle bit there. You get 2 cubed, 2, 6, 3 on the outside. So even if it's a cube, we can split up and multiply, right? The insides are multiplied. Oh, let's do it properly. That's a 3, and that's a 3. 6 cubed there. These undo one another, left with a 2. These, yeah, it's, as I said, a little out of order. This is one way to do it with some exponent rules. These multiply together, 6 divided by 3, to give you 6 divided by 3. 6 over 3 is a 2. And that gets you to the 18 that's shown there on the left side. Okay, just for fun, 4 to the power of 3, boom, 64. Negative 3 times negative 3, keeping track of the negatives, gives you plus 9. Right? Negative times a negative is positive. So the answer for the second one is plus 9. Now this one, watch. The 2 applies on the 3 only. It has not captured, the 2 has not captured the negative. So the negative is in the front. This 2 says there are 2 3's multiplied together. And it gives you a different answer. It gives the answer of negative 9. Since that negative in the front stays in the front, stays in the front, you get a 9 like that. Okay, these last 2 questions, the negative 3 and the negative 3. Ooh, those take A's away. Just for fun, they can show up in more complicated situations. So you do the square root of 9 first, looking at that first question. Square root of 9 over 6, that gives you 3. 3 over 6, you can reduce it. Final answer of half like that. This one is shown to you just to spook you, because you probably learned that you can't take the square root of negative numbers. And in grade 10, that's true. However, you are allowed to take the cubed root. That is okay. And for free, I will tell you it is a -4. And so if we want to work backwards to check, what we do is we take -4 times -4 times -4. Well, you'll get used to it, but 4 times 4 is 16, times 4 is 64. So that's just a number. But look at this. Negative times a negative is a positive, times a negative is a negative. Okay, so in fact, we are allowed to have a negative underneath because we get an answer that can get us back to where we started there. Okay, so don't be spooked if it's cubed. If it's cubed, it's probably okay. Or rather, cubed root. It's probably okay. Cubed root. All right, our little number theory question there. Is 64 squared, cubed, or both? Remember, for it to be squared, you have to be able to write it with a even or a multiple of 2. And for sure you can. 64 is the same as 8 squared. Is it cubed? Cube, rather. And this is where it's a multiple of 3. And yes, as we've seen a few times, maybe not written like this, but 4 to the power of 3 gives you 64. 4 times 4, 16 times 4 is 64. So yes, that's also true. Now, can it be both? Yes, it can be. Because remember, both has to be a multiple of 2 and 3. Means it has to be a multiple of 6. Well, if you do the factor tree that we talked about earlier, but never did, you can see pretty quick that we get 1, 2, 3, 4, 5, 6 2's all there. In other words, 64 is the same as having 6 2's all multiplied together. So since we have a 6 there, right, it's a multiple of 6. So yes, in fact, 64 is both. And a little number theory side question. All right, so let's get close to the end. We're getting close to the end. Let's finish this up, because the goal is to work with radicals, square roots. So reminder, these are opposites of one another. We saw this earlier, I think. Yeah, saw this as well. Making it big, undoing it, we're back to where we started. Same here. Remember, you can just jump right to the final answer. If a square root and a square are there, they undo one another. Done. 6. Okay, or work it out if you need to so that you get a number that's familiar, and then you're good to go. But now, here we go. Time to be professional. Multiplying square roots with one another. We saw that earlier a little bit, where we have the inside part, root 4 times root 9. Okay, the outside parts multiply together as well. So we'll see what that means with some examples. Okay, so we saw this. You can think of it as putting them together, getting something known, and then getting the final answer. Right, or You could do them separately first. Square root of 9 is 3. Square root of 4 is 2. And get the answer that way. Okay. Similarly, multiplying now, right? You can combine them together first. It's a bit big. Happens to be 400. All right. Just using the property, you're allowed to multiply them together first. Oh, this kind of mixes them. So on the left side, keeps them separate. What's the square root of 16? 4. What's the square root of 25? 5. On the right side, they do combine them together. So you get 400. And then from your brain, you can remember, square root of 400 is 20. 4 times 5 is 20. So a couple different ways to do this one. Perfect squares we saw, big list there. All right, finally onto the good stuff here. Well, it's all good stuff, but we need this bit here. What we got to do is we got to get answers that look like this. That is, get roots so that there's a number on the outside like the 3, and then there's a number on the inside like the 5. Okay, so how do you do this? Number 1, it says break down a number so you have one of the numbers being a perfect square. So I'm going to give this an example to start with. 18. So you write it, break this number down so it's 2 numbers, 2 factors to be proper, one of them being a perfect square. Well, I know 9 is on the list of being a perfect square. 9 is 3 times 3. Okay, so we separate them. That's what number 2 said. Whoops. Sneaking ahead. That stays as the 9. Just separating them to start with. Okay. Number 3, then we take the square root. Square root of 9, 3. Square root of 2 like that. Okay. Number 3 also says put the square root, put the perfect cube first so that the outside number is in the front, but you can just arrange that. Okay. Now, the inside might stay complicated. The number might be so big to start with that you have to do this process again. Yeah, so you just do it again. Okay, rewrite the inside, square it out, separate it, clean it up there. So a couple examples. First one here, gotta change 75 to a mixed root. How does that look? Well, first thing I know that I remember, 75 is the same as 25 times 3. And I happen to choose 25 because I know 25 is a square number. Separate them because they're square roots and we're allowed. What's the square root of 25? 5. Square root of 3? That's square root of 3. Finished. Final answer. This is the mixed root, mixed radical. Just change that to radical. I think they all might be like that. Okay, final answer right there. Another one, root 28. How can you rewrite the number 28? Happen to know it's 4 times 7. And so, separate them. Square root of 4 is 2. 2 root 7. Similar in style, but a little bit bigger. Don't panic. You might have to do the prime factorization for this. That's what you can do, if you're not sure. But you can get that, let's see, get that 121 showing up, which is kind of obvious. See, 484, what goes into both? 2, 242, 2, 121. 121 I happen to recognize as a math teacher. 11 squared, right? So now you can think of it like 11 squared times 2 squared. Right, so 11 squared is the 121 on the left side. 2 squared like that. Split them up. Squared undoes the 121. It's 11. Square root of 4, 2. 5 to 67. Yeah, pretty awkward. But here's a trick. If you look at the numbers on the inside, 5 plus 6 plus 7, just add them up. You get 18, which is a smaller, you get a smaller number, easier to work with. Now, does 18 divide by 3? The answer is yes. So the question is, does 567 divide by 3? And the answer is yes. So you can get started on the prime factorization if you're not sure what this number is. That's a 169 that goes in there. 3 goes into that, 226. Oh, let's check that. 3 goes in there. It's 1, 2 left over. Let's make it 189. Right, that gets you up to 24, 26, 2 left over, 27, 9. Yeah, 189 like that. Well, that doesn't look very square rooty. Let's see. Oh, okay, 81 times 7. Different way of, different order of doing it. Split them up. 9 and a 9 root 7 like that. Okay. This is probably the longest one of the bunch. How to change root 72 to a mixed root. Well, 8 and 9 are kind of obvious. So the 9 can go out. That changes to the 3. But see, this is an example. Maybe if we chose different numbers in the beginning, we'd be at the end already, but we didn't. We still have an 8 there. So all you do is just continue. Just do it again. Continue. We had the 3 and the 8. So the 8 now changes to 4. You rewrite that with a square number, 4 and a 2. 4 goes on the outside. And see, the effect on the outside is that these two numbers multiply together now. Give a final result of 6 and a 2 like that. So that is the process of changing from entire radicals to mixed radicals. Now, this is the home run. Last little bit. See, if the insides match, then you add them together. If they don't match, it's finished, or you try and change it to a mixed radical like we just did. Okay, so look at this one. On the insides, you have a root 2 here, you have a root 2, and you have a root 2 all over the place. So that means you can just add these up together. You get a 3 plus a 7, which is 10. And then minus 4 root 2. You see, so these two, you can add those together. You get 10 root 2 minus 4 root 2 like that. And what do you get? 6 root 2 is the final answer there. See, all the insides are the same, so they all can combine together. Now look at this next example. See, little trick with PowerPoint. It's the exact same, except you have a plus 6 root 3 at the end. So notice, what's going to happen is that those root 2's, they will all combine together again. Into what? Well, as we just saw, we had a 10 and then a minus 4, so we add them up and we get a 6 root 2, but we have this hanger on, plus 6 root 3. Are these the same? No. So that means this answer is finished. It's finished because these insides, they are not the same. They cannot be combined together. Okay, so finished when it's like that. Okay, keep those results separate. And so this is like the grand finale. What happened is we learned about the mixed radicals, creating mixed radicals, because this situation might come up. Okay, you might have an expression like this to work on. All of the insides are different, so it looks like finished. A root 2 is different than a root 18, is different than a root 50. But here's what has to happen actually. You change them to mixed, that is, change the radicals to mixed, and you, in fact, you might see that, oh, maybe we're not finished. Okay, this would be the second step for my thinking. Start rewriting the insides so that they have square numbers starting to appear. So nothing happening with 3 root 2. And after a while, once you get good at this, you can possibly skip this step here. But for now, just write it in. So you have the 3 root 2. Now, what's the square root of 9? 3. What's the square root of 2? Oh, I mean, just square root of 2. That stays. Here, be careful with the multiplying and all that. We got a 4. What's the square root of 25? That's a 5, and it's times root 2 there. So notice we got root 2's all over the place now. They were hidden in the beginning. Hidden inside of the 18. Hidden inside of the square root 50. Right? But from changing them to a mixed radical, we've found them out. And so now we can combine them together. 3 root 2 plus 3 root 2, that's a 6 root 2. 4 times 5, you do that first, so that's a subtract 20 root 2. The insides are still the same, so that means we can keep going to the final answer of negative 14 root 2. So what does this mean? Well, importantly, no decimals. By working with square roots, we stayed exact. We stayed precise. And that means if you think about the bridge that we were building in the beginning, hey, our bridge is going to meet right? Our bridge is going to work. If you got decimals in the beginning and started doing all that rounding stuff, ooh, struggles. Not so good. All right, good people. Well, that was quite a long one. Partly because I'm not sure what you know and what you don't. If you found the topic easy, then good. If this is the first time through, hopefully you found it informative and useful. But on the board now, you can see, or rather on the screen, are 1, 2, 3, 4 worksheets that are now fair game, that you now for sure have the skills in order to be able to complete. Okay, so check those out in Teams. In the meantime, thank you for stopping by. Hope you enjoyed it. And I will see you next time. Take care until then.